Hi class, Dr. Searcy here with the Chapter 7 video lecture for the odd numbered problems. To begin with, I just want to remind you of the title. It says that it's the probability and samples, the distribution of sample means. The reason why I want to remind you about this is because this is the important new thing in Chapter 7. This idea that we are working with a new type of distribution, a distribution now of sample means. Let me just remind you of this, right? We were saying that we were taking some population of data, right? Some population that we're interested in. And from that population, we are pulling out a sample at a time. It used to be that we would pull out an individual raw score at a time, but now we're pulling out a whole sample, right? Remember, those samples are all going to be the same size. With that, remember the thing that we're going to do with each sample that we pull out is we're going to put them now into another distribution. And so let me just remind you, the way that we're looking at each sample is with each sample that we pull out, that sample's mean score. Right? So that's what we are, that's what we're throwing into this new distribution. So that when it gets stacked up, right, it's a histogram. When it gets stacked up with data, what is making up the data? Each of those samples that we're talking about, right? That's what the bars are here. And that's why we're calling this a distribution of sample means. Okay, so with that introduction, let's go ahead and talk about each of the odd problems. Beginning with number 1. Here, this question is just basically asking for us to define some of these new terms that we're going over in this chapter. The first really important term that we have to define is this distribution of sample means. Actually, I have just defined it, right? I've been talking about it here, and I've been explaining it there. How did I answer the question, though? I said in words that a distribution of sample means is a collection of sample means from all possible samples of a particular n obtained from a population, right? So that's everything that we've been saying up here. One thing that you want to remember about that n is that all of the samples that get pulled out, they all have the same sample size. So they all have the same n. Okay, so then the second term in question 1 is the expected value of m. This term I kind of grazed over in the lecture, but basically the expected value of m, here we're saying the expected value of the sample mean, its definition is that we're saying that the sample mean of the distribution of, the mean of the distribution of sample means is equal to mu. What that's saying is that when we pull out those samples and we put them into our distribution of sample means, the mean of all of those samples is going to be equal to the mean of the population. That's this idea of expected value of the sample mean. Right? So it's that the mean of the samples in the distribution of sample means is going to equal the mean of the population. Okay, so then we have question C, where we're looking at what is the standard error of m, or what is the standard error of the sample mean. My definition for this is that it is a new standard deviation that we are going to use. The standard deviation is going to apply to this new distribution that we're talking about, this distribution of sample means. Okay, so how is this new standard deviation going to work? Basically, we're going to use this symbol to identify it. So this symbol is the standard deviation of a distribution of sample means. How do you obtain this value? You take the population standard deviation, right? The standard deviation of the population that you started with, and you divide that by the square root of the size of your samples, the lowercase n. We'll get a lot of practice working on this one. One thing that you want to know is that this is one of the focuses of this chapter, is now working with this new symbol. Okay, well, so that answers question number 1. Let's go ahead and move on to question number 3. Here the question is asking, describe the distribution of sample means, right? So it's going back to this idea of talking about this distribution of sample means. Describe its shape, its mean, and its standard error for samples of n equals 64, selected from a population with a mean of 90 and a standard deviation of 32. Okay, so they gave us a particular set of data to work with. But what they want us to do with that particular set of data is to describe the shape of the curve that it's a part of, how the mean is working here, and what the standard error is. Okay, so let's go ahead and talk about the first part of this, the shape. We're answering that here. And this is getting to a point that I made in the chapter textbook video lecture. Here we were saying that when we talk about the shape of the distribution of the sample means, it's going to be the same as the shape of the population that it came from. The population that it came from is a normal curve, right? It's that smooth, bell-shaped curve. So the distribution of the sample mean, its shape is going to be normal as well, particularly because you had more than 30 participants per sample, right? You had 64 participants per sample. And another thing that I said was by the time you get to 30, this curve is going to be normally distributed. Okay, so that's our description of the shape of this distribution of data. Now, let's talk about the mean of this distribution of data. Here, what they're getting at is we should know what the mean of the distribution of the sample means is because we know what the mean of the population is that it came from, right? So that the mean of the population was 90. So, because the two are going to equal each other, then we should expect the value of the distribution of the sample means is also going to be 90. Okay, so then there's this third part of part 3, the standard error. Now this is getting back to this. That is another name for this standard deviation. We can also refer to it as standard error. Okay, so what are we doing with that? We're saying standard error is the new standard deviation when we're talking about a standard deviation of a distribution of sample means. How are we going to get that value? We just said it here, but we're repeating it here. The standard error can be obtained by knowing the population mean and dividing it by the square root of the sample size that we're pulling out. Okay, standard deviation for distribution of sample means, now referred to as standard error. We've got a practice problem for it, right? So in the problem, they told us what the population standard deviation was. That's going to go here. They also told us what the n was. It's going to go here. We're going to find the square root of that 64. It's 8. So what we're finding here then is that for this set of data, its standard error is 4. Okay, so let's go ahead and move on to question number 5. Here we're starting off with a presentation of data. And the presentation is saying that we're working with the population. it has a standard deviation, and that standard deviation is 24. Then they're going right to our A question. Now, just let me note, for these problems, right, in this chapter, they're training you to think of doing this equation and then doing a second equation, right? So they're training you to think of figuring out what standard error is by finding the population standard deviation and dividing it by the square root of n. But once you have that value, then they're going to want to have you pop it into this new version of the z equation, right? The z equation is now where it's going to be a sample mean minus population mean over this new standard deviation, right? Over this standard error. Remember before, in chapter 5, you used to do this z equation, but whereas this was a raw score, not a mean, and this was a regular standard deviation. So just remember, in this chapter, you're trying to see first, where is the data, where is the information for this equation? How can I use it to obtain this equation? Okay. From there, let's go ahead and talk about question number 5. Question number 5, they're giving us some information. They've already given us the population standard deviation, right? And right away, you want to be thinking, where is this value important? Of the two equations, its value is in the first equation, right? They've told you what the numerator is for that standard error equation. From there, in question A, they say, on average, how much difference should there be between the sample mean and the population mean for a random sample of n equals 4 scores from this population? Now, right at this point in question A, you see these two bits of information that you've been given. Standard deviation and an n. Where do you think you should put that? You should put those two values into that equation. So that's what we're going to do. We've got our answer right here. We're saying, okay, we're going to calculate that standard error, and we're going to say it's that 24 over the square root of 4. That's going to reduce to 24 over 2, and so then our answer is going to be 12. What is it that we're saying here? We're saying that our new standard deviation, this standard error, is 12. So if we were to draw a curve, right, and we'd put our standard error underneath it, there would be a standard error or standard deviation unit of 12 spaces that you'd have to get out to that first standard error unit. Okay, so now let's look at question B. B is asking, on average, how much difference should there be for a sample of n equals 9 scores? Okay, so now at this point, you've basically just been given the same information again. You've been given an original standard deviation and now another n. So what are you going to do with that? You're going to take that and calculate your standard error equation over again. But this time, you're going to leave your 24 in the standard deviation spot, and you're going to put a 9 in your n spot. That ends up giving you 24 over 3, which reduces to 8. So then there's question C. Basically the same exact question, but now with an n of 16. So you're going to do the same thing again. You're going to find our standard error. That's going to be gotten by saying we're going to take that 24 and divide it by the square root of this 16. That reduces to 24 over 4, which further reduces to 6. Now, one thing that I think the authors are trying to show you in these problems in number 5 is what happens to your standard error value when you have these different n's in place, right? So we started out with a small n, and that led to a large standard error. As that n increased, the standard error decreased, right? To whereas you get this n of 16, your standard error is 6. So that's just one relation that you want to be seeing with these problems. But now let's go ahead and move on to our next problem, number 7. Here the question reads, for a population with a standard deviation of 12, how large a sample is necessary to have a standard error that is each of these points? Okay, so again, you need to see what information they're giving you and where that's going to fit in any equation. Right off the bat, they've given you this standard deviation, so it looks like you're going to be using that to calculate a standard error. But the only other information that they gave you was this 4 points. What's the 4 points? They're kind of giving it to you right here. They're saying, for a population with a standard deviation of 12, how large a sample is necessary to have a standard error that is each of these? So what they're saying is, this is your standard error. This is your standard deviation. If you remember the equation, I'll go right here. The equation is standard deviation over the square root of n. So what's happening here is, in this problem, they're giving you the standard deviation in the equation, and they're also giving you the standard error in the equation. What they're not giving you is n, and that's what you're supposed to figure out, right? That's where here they're asking that. How large a sample, right? What is the n going to be for this? Okay, so let's go ahead and do our calculations then. The problem starts off looking like this, right? It's supposed to be this idea of the standard deviation divided by the square root of n. So in this case, it's going to be this 12 divided by the square root of n, and all of that is going to equal that standard error of 4. So how are we going to solve this problem? What do we do here? We've got this square root of n, and we've got that 12 in the numerator, and we've got that 4 over on the equal sign by itself. The way that I solved it was, I said, you know what? I'm not going to worry about the square root of the n right now. For right now, I'm going to ignore that square root, and I'll think about that later. Instead, I'm just going to think that I have this as our equation. 4 equals 12 over n. From there, I'm going to solve it algebraically, right? My goal is to get the n by itself. And the way I'm going to get the n by itself is I'm going to move it out of this denominator and bring it over to the other side of the equation. So then it becomes 4n equals 12. Now, right, my goal is to get that n by itself. So I'm going to divide the 4 out of there. So then I have n equals 12 divided by 4, which gives me n over 3. Now at this point, now I'm going to go ahead and take care of that square root part of the n over here. The way I'm going to do it is I'm going to say, okay, the n needs to be accounted for. The way I'm going to account for it is I'm going to square it. I'm going to say that that's the 9 that's going to go under that square root. Okay, so same thing with the other 2 problems in 7. Right, so for the next one, we're saying, again, 12 is our standard deviation. This time 3 is the standard error in the problem. We are solving for n. So the way we're going to do it, so we're going to remove the square root. Just say n cancels out here times that 3, so it becomes 3n equals 12. Then we're going to move that 3 out by dividing it. So we get an n of 4. That then gives us an n of 16. Same thing with the problem for C. Now we've been given a standard deviation of 2. The problem is going to turn into 2 equals 12 over n. We're going to multiply that n out, times it over here, so it becomes 2n equals 12. We're going to get rid of that 2. Right now it's being multiplied, so we're going to divide it out. Divide it on this side, so it gives us n equals 6. And then we'll square it, so we get a 36. Maybe the other thing that we can see here is, let's see if there's another relationship. It does seem like we're seeing that relationship again between the size of n and the size of the standard error, right? The larger n, the smaller the standard error. Here, the smaller the n, the larger the standard error. But let's keep on going to now problem number 9. Here we're saying, for a sample of n equals 16 scores, what is the value of the population standard deviation necessary to produce each of the following standard error values? Okay, so they're asking about standard error here, right? They're asking for that value. Notice that they have given you the n, but they have not given you the standard deviation, right? So it looks like this time, the item that you're going to be solving for is standard deviation. It looks like they're saying it right here. Yeah, what is the value of the population standard deviation? Okay, so for problem A, they've given us n, and they've also given us the standard error, right? So they've given us this 8 right here. We're going to use those two numbers to solve for the standard deviation. How does that work with problem A? So here we're saying we have 8 in the standard error spot equals a standard deviation that we don't know divided by the square root of this 16. That's going to reduce down to, first we'll go and get that square root. So now it becomes 8 equals standard deviation divided by 4. We're going to get that 4 out of there. Right now it's being divided, so we're going to multiply it out. And when we do, right, so we multiply it out on this side, multiply it out on this side. And so that gives us this value, which is going to then give us 32 as our standard deviation. Right, so hopefully you're saying that you just really want to have a solid sense of what the equation looks like. From there, what information are they giving us? And what information can you punch in to each part of the equation so that then you're seeing that they're giving you everything except one bit. So then you're supposed to solve for that one bit. In this case, in problem number 9, it's the standard deviation that you're solving for. Okay, so for problem B, they gave us standard error 4, and they gave us the n of 16, so we're solving for that standard deviation. We're going to do the same thing. Get the square root of that 16, it's 4. Now divided by that standard deviation, we're going to multiply them both out so that we get 16 equals the standard deviation. Same thing with problem number C. Here, we're given our standard error of 1, that n of 16. We get the square root of the 16, multiply that 4 on both sides, so we end up with 4 as our standard deviation. Okay, so moving on to problem number 11. Now, here, I just want to remind you that now you're going to see the two equations that we've been talking about being used, right? So I'll just start off by presenting the two equations. First, we're going to solve for our standard error. Then once we know what our standard error is, we're going to use it as part of this new z equation, right? In the denominator of the new z equation. Okay, so how are we going to do this? First, we're saying we have a sample whose n is 25 and a mean of 68. Find the z-score for this sample. Okay, in this case, if it was obtained from a mu with a 60 and a standard deviation of 10. So, just to start off with, this problem A actually looks a bit deceiving. What I'm saying here is that we have not created a distribution of sample means. Here, we're just working with a regular population. So what does that mean? That means that we're going to bypass this equation for right now. For A, looks like they're just asking us to calculate just that old z-score that we used to see like back in chapter 5. Let's see if I'm right about that. No, I'm not. Okay, let's see. Okay. Okay, yeah. So, okay, I was totally wrong. And look how I was wrong. I was misinterpreting what they were giving me here, right? They were giving me information for the standard error. They gave me that standard deviation that goes on the top, and they also gave me my n. So I do need to figure that out first, right? Okay, so for A, I've just calculated the standard error. It's this 2. How do I get the standard error? Well, it's this 10 over the square root of 25. Now I'm going to take that standard error of 2, and I'm going to place it in my new z equation, right? That 2 is going to come right here. So then my z equation is 68 minus 60 over this 2, which gives me a z of 4. Okay, so we are doing the standard error equation so that then we can do the z equation. Let's see if that is the case for problem B. Okay, so we have all this information if it was obtained from a population with 60 and a standard deviation of 20. So yeah, first thing is we are seeing that they gave us information for the standard error equation. It was this 20 that goes right here, 25 from here that goes here. So this says that we now have this standard error of 4. That 4 is going to go in the denominator of our new z equation, where in the numerator is that 68 minus that 60. That gives us 8 over 4, which gives us 2. Right, so the z for this is 2. So then for problem C, same standard error equation to begin with. Here they're saying that our standard deviation is 40, our n is still 25, so it's going to be 40 over 5 equals 8. That 8 is now going to be the denominator of our z equation. So it's 68 minus 60 over 8 gives us a z of 1. Okay, so as we move through these problems, we're seeing this progression, right? First, we calculate standard error. Second, we calculate z, and we're able to calculate z because we have a standard error that we got from that first calculation. Okay, so moving on to number 13. Here it says, scores on a standardized reading test for 4th grade students form a normal distribution with a mean of 60 and a standard deviation of 20. What is the probability of obtaining a sample mean greater than this mean equals 65 for each of the following? Okay, so now at this point, I'm seeing that we do have to run through both equations again, right? So just to remind you, first, the standard error, which is the standard deviation divided by n. That's going to give you the information for z, which is the sample mean minus the population mean over that standard error that you've calculated over here. Okay, so let's see how we can punch all that into our equation for A. To begin with, right, we're trying to figure out what our standard error information is. We've been given that standard deviation, and in A, we've been given our n. So we're going to use that to calculate our standard error. It's that 20 over this 16, the square root of the 16. So that gives us 20 over 4, which gives us then a standard error of 5. Okay? Standard error of 5. We're now going to use the standard error of 5 in our z equation. Right? So here's our z. 65, where's that 65 come from? It's that sample mean minus this population mean over that standard error of 5 gives us 5 over 5, which gives us 1. But now we've got this third step, right? So we say that our first step was we first calculated the standard error. Then second, we calculated z. Now we're going to do this third thing, but this third thing that we've been doing since like chapter 6. And that third thing is we're going to look up Z in the unit normal table, right? Where we look at like the proportions of the body, the tail, or that distance from the mean to the from the specific Z to the mean. Okay, so I think that we have to do this third step here. Yeah, right, because the question that was being asked for question A, what is the probability of obtaining a sample mean greater than 65 for each of the following? So, what is the probability of obtaining a sample mean greater than 65? Right, so in this case, we're thinking in terms of 65 being there on the x-axis, and we want to know what is that space, that proportion, greater than 65. So we went and looked it up. By the way, this is the tail section, the proportion that we're interested in. When we go look that up, we see that the percent or the proportion is 1.1587. Okay, or 15%, 15.87% of the curve. Okay, so one thing that you want to remember from here on out is you may be asked questions in terms of these three steps now. First, calculate the standard error so that you can calculate Z, so that then you can look Z up in the unit normal table and look for its proportion of interest, tail, body, or that D section. Okay, so let's see how this applies to problem B here. First thing that we're doing, calculating that standard error. Here it's 20 over 25, right, the square root of 25, which gives us a standard error of 4. We're going to use that standard error in our Z equation, where it's that 65 minus that 60. Gives us 5 over 4, which gives us a Z value of 1.25. But again, the question is that probability of finding that chunk that's greater than 65. Now, our Z is 1.25, but we're still being asked about the same part of the curve. So we're still going to go look for the tail, but now at a Z of 1.25, and that gives us a tail section of 0.1056. Okay, so same thing with problem number C for this problem. First thing is our standard error equation. Here it's 20 over 100, 20 over the square root of 100, right? And we're getting that 100 right there. We're getting that 20 right there. So that all reduces to 2. We're going to use that 2 over here in the denominator of our new Z equation. That reduces to 2.5, right? So this is the Z that we're now going to go look up. We're doing the same thing in terms of the curve. We're still looking for the tail of the curve, but now where the Z is 2.5, and so that's now going to be this 0.0062. Okay, so main thing to remember here is that you want to see how to do this equation, then this operation. Let's see if that applies in problem number 15. Okay, just to start with, let's look at the problem. It says you have a normal distribution with a mean of 54 and a standard deviation of 6. What is the probability of randomly selecting a score less than x equals 51? Okay, now here is a question that's tricky for us, right? So we've been talking about describing these curves with the sample means in them, right? This distribution of sample means. In this question, though, they actually aren't asking about this yet. In this question, A, they're still talking about the usual sample that we used to talk about. How do I know that? Because of this part right here, right? They're not saying a mean score of 51. They're saying a raw score of 51. So they're still talking about those old curves that we used to talk about before. So what does that mean? What does that mean? That is telling me that this time for A, we're not going to calculate this standard error. We're just going to find the answer to the question the way that we had been doing like in chapter 6. Okay, so how are we going to do that? How are we going to do that? First, let's just remember those are our two equations of interest. For A, it looks like we're not going to use this Z equation. For A, it looks like we're going to go back to the old Z equation, which was a raw score minus a population mean divided by a regular standard deviation. Why am I suspecting that we're going to use this equation instead of this equation for A? The reason is because they're giving us an X, not an X bar. Okay, so let's see what happens with that. Basically, what we got is I'm going back to using this equation again. So I'm going to fill in the parts of that equation. I'm seeing that I've got an X value of 51. I've got a population mean of 54. And I've got a regular old standard deviation of 6. Right? So they gave me everything I needed to fill that equation out. Let's go ahead and solve it. It ends up giving us -3/6, which reduces to a -0.5. Okay, so now what you want to see, that's the Z that we've been given, this -0.5. What's the question that's being asked? What is the probability of randomly selecting a score less than X equals 51? So let's just think about what this curve is going to look like. Okay, so for problem A, what I'm hearing in the question is in our curve, they want to know about this X value of 51. What they want to know is what is the probability of randomly selecting a score less than that, right? So when we're thinking about our shaded portion of the curve then, we're thinking in terms of everything less than the 51. So now, based on everything you've been told so far, right, you've just found a Z value. And so you have to engage in this step of going to the UNT and seeing the proportion for that Z. In this case, when you go to look up that proportion for that -0.5, you're going to look in the body. Why the body? Because of how much area is taken up. A whole half plus some, right? That's the body of the curve. And so that's why we have this value of 0.3085. By the way, I'm also noticing that that -0.5 is somewhere out here, right? It's somewhere below the mean because it's a -0.5, which also is interesting. And now I think I just made a mistake. I'm gonna check something here. Did I screw up again? Okay, so what we're gonna do right now to see if Dr. Shirsi screwed up is we're gonna go look up this -0.5 and we're gonna see where is that 0.3085. Is it in the body? Now I'm starting to think it's in the tail that we're supposed to be looking at because we're looking at what's less than this. So not body, gosh darn it, but tail. And let's see if that's right. Okay, so the Z value is 0.5 because we don't care about negatives. I have that Z of 0.5 here. And yes, gosh darn it. As it turns out, we are looking in the tail. Why am I seeing right now that we're looking in the tail? Because we're being asked what is less than -0.5, right? And so when we draw the curve for that, that is a value that's right there. And so if it's less than that value, we're talking about that chunk of the curve. That's the tail of the curve. Okay, hope I didn't confuse you. But now let's go ahead and look at the other problems for 15. For the rest of these, for B and C, I think now we're moving away from doing our old style Z Now I think we're going to go back to doing these two. Let's see. For B, it says, what is the probability of selecting a sample of n equals 4 scores with a mean less than 51? Okay, so yeah. Now we're going back to this idea of us talking about a distribution of sample means here. How do I know that? Because we pulled out a sample, right? We selected a sample. We didn't select a score, we selected a sample. And that sample had 4 people in it, and we're saying what's the probability that its mean is going to be 51. Okay, so that means we're going to have to find standard error, this new z, and then probably look that z up in the unit normal table. But let's see how we did it. We're going to see if we can do this equation first for problem B. And let's see if that happens. Yeah, so we were given this 6, which is the standard deviation, and we also were given the n, which is that 4. So we got the square root of that 4. It becomes 6 over 2. And so now we're saying that we have this standard error of 3. Okay, so we did the first equation. Now we're going to use that 3 in our second equation, this z. But where is that 51 and that 54 coming from? Right, it's a sample mean minus the population mean. Our sample mean is that 51. Our population mean is that 54. That's our standard error that we got over here. So that's going to reduce to a negative 3 over 3, which gives us a negative 1. The question is asking, right, so with a mean less than that. So now I guess I shouldn't draw the curve until I know what my z value is. So now I'm going to go and draw the curve. I see that my mean value is this negative 1. And the question they're asking is, what is the probability of selecting a sample of scores with a mean less than that? Right, so if it's less than that, it's going to be that section of the curve. That's the tail section. So what am I going to do? I'm going to go to my unit normal table. I'm going to look up that z of 1, and I'm going to write down whatever is in the tail section of that. That's that 0.1587. Okay, so let's see what happens then with problem C. With C, they're asking what is the probability of selecting a sample? Okay, so it's distribution of sample means again, with an n of 36 and with that score, with that mean of 51. Okay, so I'm going to start off calculating our expected, our standard error. What is that? It's this 6. Where did that 6 come from? Oh yeah, it's the standard deviation divided by the square root of our n. That reduces to 6 over 6, reduces to a standard error of 1. We're going to use that 1 in our new z equation, where now it's 51 minus 4 over that 1. That reduces to negative 3 over 1, which reduces to a negative 3. Right? So again, now at this point, I know what my z value is. I can draw my curve for it. And I'm saying that again, it's a negative value. And it's pretty far from the mean this time. And again, we're being asked about the less than that score, right? So again, it's going to be less than that z. So we're going to go to our unit normal table. We're going to look up 3, and we're going to figure out what is the proportion in the tail when we have a standard deviation of 3. Now, let me just kind of point something out about this, right? So I'm saying, I just go to the standard deviation. Remember that's what's happening here is you have this z value of negative 3. But it also maps on to any standard deviation value of negative 3. So what that's saying is that whatever number you have here, it's way out, away from the mean. How are we saying that? It's this many standard deviations as it's right. This would, if it's a standard deviation we're talking about, it's just a 3. then it would just be a 2. Here would just be 1. But in terms of Z units, it's a -2 and a -1. So the point that I'm making here is that this spot is really far away from the mean. It's not just 1 standard deviation unit away, not just 2 standard deviation units away, but 3 standard deviation units away. That's really far. And another thing that I should tell you is that this space is going to be really, really small, right? Because it's so far out. It's just a small chunk of the curve. Let's see if that's right in terms of our proportion. And yeah, that's right, right? So this is only 0.0013 of the entire distribution. Okay, so let's go ahead and now move on to question number 17. And this, I want to get a fresh sheet to not distract you with. Okay. But I'll go ahead and hang on to this other sheet too, right? So I'm saying that this flow of work is how we're trying to think of solving each of the problems that we come across. So let's look at how this might fit into question number 17. Here we're saying that for random samples of size n equals 25, selected from a normal distribution with a mean of 50 and a standard deviation of 20, find each of the following. The range of sample means that defines the middle 95% of the distribution of sample means. Okay, so with this, first thing that you want to remember is what they're talking about when they say something like this, 95% of a distribution of sample means. What they're saying is we want to know what is the range of the distribution where we're saying we want to know what the middle 95% is, right? And that's what this is. That's the middle 95%. So they want to know, okay, the range of sample means. So basically, on one end, they want to know what is the sample mean value that would go right here. And on the other end, what is the sample mean value that would go there, right? This is a distribution of sample means. We pulled a bunch of sample means out of a population to create this distribution. Now on our X line, sample means are our X values. So all they want to know is what's the sample mean that goes at this end and what's the sample mean that goes at that end. So how are we going to figure that out? How are we going to get that information? Well, the way that we're going to get it is we're going to first think in terms of what's the Z that is here and what is the Z that's there. The way that we're going to do that is we're going to think in terms of where this 95% is in terms of boundaries, right? Okay, so we're going to go back to thinking 95% is this entire chunk. What we want to know is what is half of a chunk for that entire 95%. And what we discover is that it is a negative 1.96 here, right? That's the Z for it, this negative 1.96. And on this side, it's this positive 1.96. How do we know that that 1.96 is the value there? Well, the way that we know is if we go to our unit normal table and we look up 1.96, we see that in our tails, we've got this much proportion, this 0.0250, right? So it's saying that you have 0.0250 here and 0.0250 here. How do I know that that's 0.0250? Well, the way that I know that is the middle is 95%. So that means that on the two tails, you've got the other 5% of the entire graph, right? So the entire thing is 100%. That middle part is 95%. What's 100 minus 95? It's 5%. How is that 5% spread in this curve? Well, that 5%, half of the 5% is here, and half of the 5% is here. What are each of those halves? That's that 0.0250. So if I know what the tail is right there, right? That the tail right there is that 0.0250, then I know what the z value for that spot is too. I know that at that spot, where that's that boundary of the 95%, at that spot, the z is 1.96. Right? So that's why I'm saying it's a negative 1.96 on this side and a positive 1.96 on this side. Okay, so now at this point, we have a z, or at least the beginnings of a z equation, right? So we have the beginnings of this z equation. How do we have the beginnings? We know what the z is. Now, we need to look at, well, what other information do we have here? Well, we also know what our population mean is. They gave it to us here, right? It's 50 there and 50 there. But the value that we're being asked about is this sample mean in each equation, right? So the range of sample means that defines the middle distribution of the sample means. So we're asking, what is that range of sample means? What is this n, right? What does that sample mean? And what does that sample mean? Okay, so the other number that we need here is our standard error. Here I'm saying it's 4. But how did I get that 4? Well, the way that I got the 4 was I had to first do the standard error equation to get it. But the question gives us the information that we needed to get it, right? So the standard error equation is this 20 standard deviation over this square root of n, which is 25, right? That reduces to 20 over 5, which reduces to 4. So that is how I got my 4 here and my 4 there. Now, at this point, I have figured out all of the different numbers in each of these z equations. The only number I have not figured out is that sample mean for each one. So at this point, that's our job. We're going to now solve for what that sample mean is by isolating it. First thing I'm going to do is get rid of the 4 here, right? So right now it's part of a division problem. I just want to make sure. Yeah, so I believe that I multiplied that 4 out. I'm just going to make sure that that's what I did. Let's see. Okay, so multiplied it out on this side. So then 4 times 1.96 equals, yeah, that's 784. And so here it's a negative 7.84 because of that negative sign. Over here it's a positive 7.84 because of that positive sign. So then, right, so canceled out there, multiplied it there, canceled out here, multiplied it there, and so that's how I got the 7.84 on each side. Now I have this equation where I'm still needing to solve for our sample means. The way I'm going to do it this time is I'm still trying to isolate that variable. Here I'm going to add the 50 out because it's being subtracted, so I'm going to add it on this side. Same thing on this side, it's being subtracted, so I'm going to add it out, cancels, cancels. And when I do, that ends up giving me a mean of 42.16 on this side and a mean of 57.84 on this side, right? So this mean is the mean that goes right there, and this mean is the mean that goes right there, right? And so that's your range that question A is asking about, the range of sample means that define the middle 95% of the distribution of sample means. That's the 95%. That's one mean at one end. That's another mean at the other end. How did we get those values, right? We went through and we figured out how do we figure out what our standard error is and how do we figure out what our z value is. From there, we were able to get each of those sample means. Let's see if the same kind of logic applies to now our question B. Here this time, instead of being asked about 95%, they're asking exactly the same thing, but where it's 99%. Right, so the curve's going to look a little bit different this time. This time, 99% of the curve is accounted for. And so what's 100 minus 99? It's 1. So 1 is what you have split between here and there. Right, so that's why I've got this 1% right here. What is half of 1? 0.5, right? Or 0.05, right? 0.05. Let's make sure. Okay, 1 divided by 2. Oh, 0.5. Okay, let's see what we got here. Let's see what we got. So what I have is a z value of negative 2.58 on this side, right? So we're saying that's the z that's right here, and then a z value of 2.58 on that side. Let's look up that z and see what it is in terms of our tail section. 2.58. Yeah, so it's here I'm saying it's 0.0049. That is what is going to go right there, that point. Not 0.05, but 0.5. Yeah, 0.5. Okay, so we have just figured out what our z value is on this part and our z value on this part. Right, so again, right now we're looking for this z equation. We already also know that our population mean is 50, right? So we can put that 50 into each of those two equations. We also still have the same standard error that we had before, right? In problem B, we still have a standard deviation of 20 and an n of 25. So that still gives us this standard error of 4 here. So now at this point, what we're doing is we're figuring out what is the sample mean value that's going to go here and what is the sample mean value that's going to go here. The way that we're doing that is in each of these equations, right? There's our variable, our sample mean in each of the equations. So right now we're just solving for that x bar. First thing I'm going to do in each equation is I'm going to multiply the 4 out, multiply it by that negative 2.58, multiply it out here, multiply it by that positive 2.58. So for the first equation, it gives me negative 10.32 equals x bar minus 50. So what we're going to do is we're going to get that x bar by itself by adding that 50 now to both sides. And so on this side, it's going to be 39.68 is your sample mean, right? So it's that edge. And then for the other problem, it's now a positive 10.32 equals x bar minus 50. So that 50 is going to get added out, cancels there, add it here, so that it gives us 60.32, right? So one boundary of our 99% distribution is a sample mean of 39.68. The other boundary is a sample mean of 60.32. Okay, so moving on to problem number 19. Now we're saying jumbo shrimp are those that require 10 to 15 shrimp to make a pound. Suppose that the number of jumbo shrimp in 1 pound bag average a population mean of 12.5 with a standard deviation of 1 and forms a normal distribution. What is the probability of randomly picking a sample of n equals 25 1-pound bags that average more than a sample mean of 13 shrimp per bag? Okay, so what we want to see first, like what's going on with the curve, right? They want to know what is the probability of randomly picking a sample of n equals 25 1-pound bags that average more than 13 shrimp per bag, right? So basically, we're looking for this section of the curve. There's our 13, our mean of 13. We want to know what's the probability of getting something more than that 13. Okay, so how are we going to do that? First, let's think about the two equations, right? And what information did they give us with regard to the two equations? Well, I see a standard deviation right there, and I also see an n right there. So they've given us the two values for our standard error. For the z equation, they gave us this x bar, right? And that's this value here. They also gave us a population mean, but notice they did not give us a z or a standard error. So again, what we're going to do, we're going to calculate the standard error, so we have it here, so we can use these values to solve that z, and then look up the unit normal table. Okay, so first things first, let's solve our standard error. We're looking for these two values. I see them, right? So there's our equation. I see them right here. It's that 1 over this square root of that 25. That reduces to 1/5, which further reduces to 0.2. Okay, so that 0.2 is our standard error that we can use in our new z equation. So we're going to go ahead and pop all the numbers into our new z equation. Right, so there's our formula. The 13 is that mean. The 12.5 is the population mean. The 0.2 is our standard error that we just calculated. So now at this point, it's this subtraction problem over this 0.2. Let's take care of the subtraction problem first. Ends up with 0.5 over 0.2. That reduces to 2.5. Okay, so now 2.5 is your z value. That's the value that you're going to go look up that we're saying is underneath that 13. Okay, so what's the p that we're going to end up putting there? Let me just look it up real quick. A z value of 2.5 is, I've got that 0.0062. Let's see if that's right. Yeah, that 0.0062. So we're saying, again, we're out a z of 2.5, right? So that's the z unit, but it's also how far we're out in terms of standard deviation units. 2.5, that's way out in the extreme. That's why the area in that area is so small. Okay, but now let's go ahead and move on to problem number 21. Again, we're thinking of these three operations. First, can we figure out that standard error? Then can we use that standard error to figure out z? And then what do we have to do with the unit normal table for that? Okay, so first, a normal distribution has a mean of 60, population mean of 60. That's going to be valuable there. And a standard deviation of 18. That's going to be valuable there. For each of the following samples, compute the z-score for the sample mean. Okay, so we have to compute a z-score. So it's going to be this for the sample mean for that. And determine whether the sample mean is a typical, a representative, or an extreme value for a sample of this size. So with that, remember what they mean by representative. This is going back to the idea of thinking in terms of standard deviations. a score is representative if that score is within one standard deviation of the mean, right? So it's representative if it's anywhere in here. Representative in the sense that it is closer to the mean, it more resembles what's going on with the rest of the group. An extreme score would be one where, let's say, you've got your standard deviation units. You go out 1, you go out 2, you go out 3. An extreme score would be a score that's more in this region, right? Towards the tail of the distribution. So basically, now we're going to be asked to find these sample means, and we're going to be asked to find, is that mean representative? Is it within one standard deviation, or is it extreme? Is it on the other side of one standard deviation? Okay, so how are we going to do that? To begin with, we're going to see all the data that all the information that we've got. In addition to getting the population mean, population standard deviation, we have these two individual problems where we get a sample mean and a n. Okay, so again, you're thinking in terms of order of operations. First this equation, then this equation. So from here then, what are the values that we can use in that first equation? Well, the values are that 18, that standard deviation, over that 4. That's going to reduce to 18 over 2, which then further reduces to 9. Okay, so 9 is your standard error value that you're now going to use in your z equation. So now at 67, where's that 67 coming from? That's that sample mean minus this population mean over this standard error. That gives you 7 over 9, which reduces to 0.78. Right? So now, with this, the other thing that you want to remember is we're talking about all this in terms of z's. Let's just remember that we were talking in terms of standard deviation, right? We were talking about like being either one standard deviation unit out or being multiple standard deviation units out. The reason why we can use z to answer this question is because z-scores map right onto standard deviation units. So that 0.78, it's about right there. It's within one standard deviation, therefore that 0.78 is representative. Okay, so let's go ahead and look at problem B for this. Again, first thing that we're going to do is calculate our standard error. It's 18 this time over 30, the square root of 36. Reduces to 18 over 6. And that reduces to 3. So now 3 is your standard error that you're going to use in this new z equation, where it's 67 minus 60 over that 3. That reduces now to 7 over 3, and that reduces to a z of 2.33. Where is that in terms of your standard deviation or your z's? Well, if we have a z of 2.33, that's out here. That's out in the extreme. Okay, last problem. Problem number 23. Here the question reads, a normal distribution has a population mean of 65 and a standard deviation of 20. For each of the following samples, compute the z-score, right? So we're going to be calculating a z-score for the sample mean. So we're going to have the sample mean in the formula. And determine whether the sample mean is a typical, representative, or an extreme. Okay, so it's basically same exact question as number 21. So again, we're going to run through the standard error equation, then the z equation. Notice for this, we're not having to do step 3, right? We're able to answer the question based on whatever z it is that we get. Okay, so first, our standard error equation. That is going to be this 20, because of standard deviation, over 4. because that's our n, or over the square root of 4, because that's our n. That reduces to 20 over 2, which then reduces to 10. That 10 is now your standard error that you're going to use in this z equation. We've got 74, that's our mean, or our sample mean, minus your population mean of 65, over your standard error of 10. That reduces to 9 over 10, which further reduces to a 0.9. Where is that? 0.9 is right here. It's within that one standard deviation unit. So that 0.9 is therefore representative of the group, of the sample. Okay, now problem number B, where we have a mean of 74 with a sample size of 25. Here we're saying first thing we're going to do is going to calculate that standard error. It's 20 over that 25, over the square root of the 25, which reduces to 20 over 5, which reduces to 4. So that's our standard error in this z equation, where we're saying 74 minus 65 over that standard error gives us 9 over 4, which further reduces to 2.25. Question is that extreme or is that representative? Well, based on what we see here, right, 2.25 would be, again, right in that section. So this is an extreme score. Okay, that is everything. Thank you very much.